Hello, this is the first part of the chapter 2.8, and we will talk today about the subspaces of Rn. And you probably already noticed that the chapter 2.8 is included in quiz 5, but it does not include it on the test. So there is no practice problems for chapter 2.8 because you're not going to be tested on this chapter. We will explore these ideas in the later chapters. And right now, all I want you to just to become familiar with ideas and definition of subspaces and get the basic techniques to work with them. We will, after we develop this intuition in the chapter 4 and 5, we will actually go in depth on these ideas. But okay, let's just look what's the subspace is. And this is such a big idea and it's used in every area of mathematics. If you already took, for example, the real analysis or complex analysis, you're probably familiar with this idea. But let's just start. What is a subspace? Anything, any set of vectors which satisfy three simple properties. First, this set of vectors should contain a zero vector. Zero vector always included in a subspace. Second, if we have two vectors in our subspace, their sum also has to be in a subspace. Finally, if we have a vector in our subspace, if we shrink or contract them, contract this vector by multiplying by the constant, this modified vector is also should be in our subspace. So it is pretty simple definition, but extremely powerful. For example, let's just look at, two vectors, randomly arbitrarily selected vectors v1 and v2 from n-dimensional space. And let's see if the span of these vectors will form a subspace. And we know that the definition of span is like all linear combinations of two vectors. So let's see if we can satisfy our three properties. Let's start from the first property. Is zero space is in the span of two vectors? And answer is yes, of course. We're looking at the all possible linear combinations of our vectors v1 and v2. So zero linear combination with zero weights is also included in span. So it's and the linear combination with zero weights will give us a zero vectors. So, okay, the zero vector will always be in the span of two vectors. Let's look at the second property. Is sum of two arbitrary vectors from all possible linear combinations of two vectors will be included in our subspace? Let's try to be very formal about it. So let's take random vector u from our span of two vectors, which is just arbitrary linear combination of this vector. And let's take vector v, which is another linear combination. And let's see if their sum will be still a linear combination. And we can use the property of linear combinations, which we discussed in the early chapter. And it's allowed us to take the constants out and write it down, the sum of our two vectors, as yet another linear combination with the first weight S1 plus T1, and the second weight will be S2 plus T2. So yes, the sum of the linear combination is also linear combinations and included in our subvector of vector spans. Okay, let's look at the third properties. So if we have a vector which from our span, and let's see if the multiplication of this vector by arbitrary constant c will still give us a linear combination. And you probably suspect that it is, because again, we can distribute our constant among the linear combination parameters, and we will get just the weights now slightly different. So our first weight will be just the product of our constant and the original weight, and the second will happen with the second weight. So, okay, all three properties seems to be true. So we can conclude that the span of two vectors is a subspace. And by the way, we can repeat this definition for as many vectors as we want. So the span of any number of vectors will form a subspace. But writing this series of vectors is not really very convenient. We like to combine multiple vectors in the matrix form. So is the span of the vectors included one in the single matrix will form a subspace? And the answer is like, that depends on the matrix, but it's probably is. So, and we will choose even the special terminology to determine the linear combinations of formed by the columns of the matrix. And we will call this a column space. So basically we take the matrix, any matrix, and we are combining the columns into the linear combinations and denoting this as a column space. So basically the span of the vectors in a given matrix we will call a column space. So is that set of linear combinations will be the subspace? Probably it is, and even better, we can use this column space to solve yet another way define the solution of systems of differential equations. For example, let's look at the column space formed by this matrix A. And let's take the vector B, which has also three components. And let's ask ourselves, does this vector B belong to the column space of matrix A? Sound like intimidating questions, but if we're looking at the definition of column space, which is just a linear combination, we can ask this question slightly different. Is vector B is a linear combination of columns questions A? Can we answer these questions? Of course we can, because before we look at our matrix property and we find that every time the non-homogeneous solution has equation has a solution, it means that we have a linear combination. So we can just take our matrix and find the solution given by the right-hand side B, and that gave us an answer. Okay, let's write down our augmented matrix. Oh, and I'm sorry, there should be a small b, not a capital one here. Okay, so we take our matrix A and add the one column of vector B to get the augmented matrix. And again, if we were trying to find the solution, the best, easiest approach is to write it in the echelon form. So first we are getting rid of this two entries of the first column to get them 0. Then we will tackle the second one, and pleasant surprise, our matrices actually have a 0 row on the bottom, which is really great. We know that our solution exists. Then another good news is that we seems to have a free variable here. So there is no third pivoting element in the third column. So the answer is, intermediate answer to this question is, the equation AX is equal B has a solution. It actually has multiple solutions. And since it has a multiple solution, we can say that the vector B is a linear combination of the columns of A. And because vector B is a linear combination of the columns of A, we can use the definition to say, yes, the B belong to the column space of the matrix A. Okay, and now I would like you to go to the end of the chapter 2.8 and solve a couple of practice problems when you are trying to determine if vector belong to the column space.